one thing that I like to describe in introducing this product is the various unit operations in the traditional scientific experimentation lifecycle, starting with design, where a scientist will envision a particular experiment or parallel experiment to run, defining the materials and the role of those materials in an experiment. Once I have a design and materials described, I transition to a physical plan. So going from a conceptual design to a physical plan requires the description of the experiment layouts. So for example, container dimensions, locations, and the like, where specific materials that I've prescribed in the design need to be in that physical layout, as well as material amounts, along with the physical operations that I'll perform while executing the experiment. When I transition from a planning phase of my experiment to execution, I need to furnish various robotics equipment with machine instructions. Finally, upon completion of the experiment, I'll prepare analysis samples. I could even prepare analysis samples for in-process characterization of experiments, ultimately culminating in an analysis step, which requires a digital design along with the data file to be integrated somehow. And then ultimately, once I've performed that integration, being able to make decisions, right? And whatever is relevant for your specific scientific integration. What we have found is that in between these unit operations, that data has to be transposed between software systems. And what we find is that in order to perform that that integration without dedicated software systems, you use abstraction and pushing data into things like applications like Excel in order to make effective decisions. What we've also found in working with our early adopters of this platform is that they will end up spending more time transposing data between software systems than actually executing experiments. And so what we hope you'll see today is a way to reduce that time of spending time in between software systems and spend more time performing and executing experiments, ultimately accelerating some of your drug discovery and drug development project timelines. So in terms of what we'll describe today, the challenge, traditional high-throughput experimentation workflow flows, so to speak, as follows. So we'll start with, as I described before, defining our experiment materials, their roles as well, along with operations and the physical layout. We'll define also our operational variants. For example, if we're going to run specific reactions at different temperatures or pressures or different time domains, we can prescribe that. We'll need to prescribe that as well. Of course, based on the materials we'll use and generate during our synthetic experiments, we'll define a set of target analytes that includes starting materials, intermediates, reaction products, unintended products like impurities, right, or side products of reactions. We can define that target list. We'll need to define that target list. We'll also need to define, in addition to the physical layout of our experiments, our analysis plates that will usually prepare samples from our reaction materials and generate analysis samples. We'll probably need to define the layouts of those analysis samples and ultimately be able to relate our analysis plate information back to our reaction information. We'll also need to facilitate the execution of the experiment. Of course, prepare those analysis samples as a part of overall experimental execution, and then execute analytical experiments like UPLC-MS as a common example. We'll also need to perform either batch-based or fully automated processing of that data with the material imports, for example, defining our analyte list for each physical sample and have that in mind as we perform that analysis, and then provide some sort of batch output for the analysis results, things like area percent or conversion factors, things like that, and relate those back to conditions. So ultimately we can make decisions on, for example, what is the best combined set of conditions that afford the best reaction outcome, as an example. So as I described before, Katalyst D2D is purpose-built to support scientists that are performing high-throughput experiments. but built in a different way than what you may have seen historically from ACDLabs. I'm sure you've for those of you familiar with ACDLabs know one of our core capabilities is the support of analytical data coming from various instrument techniques, instrument types, as well as formats that vendors prepare for those instruments. So this is a web-based application, I'll first say, and it's purpose-built to have some flexibility in layouts and workflows. Okay, so it starts with a set of what we call function widgets, which are the discrete containers that support various functions in the application. Okay, those can be arranged in a layout, and so we orient those in a layout, and there's also some prescribed, what I call widget interactivity, which Kevin, during his part of the presentation, will provide an actual demo of the interaction between widgets. Those collections of layouts are then organized by a workflow ribbon, where the chevrons in the workflow ribbon allow you to step through different aspects or operations in the experiment as you're working through it, either in design, execution, or all the way through to review and finally completion. Okay, so just an example of a customary workflow is described in the screen I have I'm showing now. Okay, so let's start with design and what that looks like. So most of us that are chemists use a certain symbology to represent our experimental design, as with reaction arrows and the position of materials relative to the arrow define a specific role. So the visual layout has meaning, and for most chemists. So we replicate that within the application. So there's a reaction design widget. There's also then anything that you add to the reaction design will build a material table. So as I click on the plus sign in the reaction design widget, I get a pop-up form that allows me to define how I'm going to add materials. So I can, of course, draw a chemical structure. I can perform a query, which I'll show the pop-up form for query in a moment, or I can also import an SD file with a set of materials corresponding to a particular material class. If I were to click on the query button, I get a pop-up with a material query search interface. That search interface, I can pick different sources. For example, we have an internal, what we call record set of materials, but we do also integrate out to various external inventory systems with who we've implemented with in terms of customers. You have the ability to connect out to their internal inventory systems, and that includes substance registration systems if you want to bring in product structures and things like that. Okay, so upon performing a query, there's a variety of different query inputs the system will support, like structure, so structure similarity or substructure searching. We can also search a variety of metadata fields to obtain, ideally, the structures we want to add to our design. Okay, so what that looks like in terms of a big cake, in terms of a reaction design, here's a traditional example of performing a condition screen for a particular reaction, and this is a coupling reaction. It's a really simple one, but just to show you an example where I've grouped materials by class. So I have 2 starting materials, a product structure and an impurity, and then a combination, and in this case, of reagents and solvents that I'll screen to determine what is the ideal combination of reagents and solvents. As I've built up this reaction design, I generate a set of material tables that I'll then use in physical planning. And just to show you some variation on how we visualize the reactions design interface, I can convert those to just structures without boxes, and I can tab through the different structures that I'm using for my synthetic experiment. Okay. As I said before, going from utilizing the material table, I can then simply drag and drop and prescribe locations of where materials will go on a reactor block in this case. And it's as simple as clicking, selecting materials that I'll add and prescribing them to single wells, single entire columns or rows or blocks or the entire plate. All right, Kevin will show some of this later. Moreover, I can prepare stock solutions of materials. And this works the same way, where I click and drag from the material table to my mixture widget, as it's called. And as I'm adding components to either mixtures or to physical locations, I can define the amount of material that will be added in a variety of different dimensions, right? So I can add by volume or by mass or by molar amount or even by equivalence if I've established a limiting reagent for a particular reaction. Okay. Moreover, the ability to create mixtures and auto-name those mixtures based on mixture constituents and concentrations is available in the software. Moreover, I don't necessarily have to create all the mixtures manually. There is the ability to clone the first mixture that I've created and then add additional materials to those clone mixtures if I need to. What I also have is the ability to, as I'm adding materials, the system, Katalyst, is preparing procedure lists so that I can facilitate execution in a facile manner. So once I've added materials, here's a representation of this experiment on a 96 well plate reactor block. I have as I've added those, this procedure list is being generated for me automatically. So the amounts of materials as I've prescribed them and what locations in the reaction array. Okay, now note also that as I'm executing the experiment, I can use Katalyst D2D to add commentary. I can add date stamps, time stamps, things like that. I can also add, attach files to an individual procedure item, where if I have, say I wanted to take a picture to denote a particular observation, and I wanted to attach that, I can do that there, okay? Similar to material additions, I can also prescribe operations in my design. So on the bottom left-hand side of the screen there, you'll see an operations list that is an editable table. So if you have specific terminology or specific operations in your lab that are unique to your lab, you have the ability to add those. But it works in a similar way where if I take an item in the table, I click and drag to the layout, and from there I can prescribe parameters for that specific operation that I want to perform. So in this case, if I want to stir, right, I can define a rate, speed, and a duration for my stirring, and it works the same way for other operations. So at this point, it might be good to transition to Kevin and have Kevin describe the utilization of Katalyst in the lab and Kevin's day job and how scientists at Celgene and now BMS are using the application today. Kevin, over to you.
All right, thank you, Andrew. All right, well, good morning, everyone. And as Sanji said in the introduction, my name is Kevin Arndt. I am a process chemist at Bristol Myers Squibb, but I was originally with Celgene before the merger last year. So I wanted to take the opportunity this morning to demonstrate how we have utilized Katalyst to really build up a high-throughput experimentation capability at Celgene, whereas prior to my joining, we were building up the capability and didn't really have all of the technology that some larger companies have. So I don't really need to go into the motivation for why we'd want to build up this capability, but very briefly, it's to accelerate timelines and deal with the more complex molecules that are coming into our pipeline. So typically in a process department, you have some drug substance target that comes in, you do some process work with it until you encounter a problem, and then you do a variety of screening and surveying to analyze the number of variables that are dealing with that process. And so you come to some decision and finally a scale up. And the majority of work is spent in this kind of screening and surveying landscape because no single synthesis is the same, and new reactions, workups, and processes need to be invented for each step. So the legacy Celgene process department realized that high-throughput experimentation could really be a benefit in that it could increase the speed of this screening and surveying efforts and increase the efficiency of our chemists and engineers, and ultimately to enable the faster study of these complex chemical questions to ultimately arrive at an informed decision. So the impetus for building this capability was clear. The challenge was, how do we implement this capability in a small department? Remember, before we were BMS, our entire department consisted of about 20 people working on all of our projects. And so the challenges for adoption of the HTE platform are kind of boiled down here. Really, there's no blueprint for kind of how to think about implementing and designing a high-throughput experiment. As I mentioned, we're a core team of scientists and engineers developing all of the processes on our projects. So we don't have the space or the resources to implement specialty groups that would be dedicated to such a technology. So we realized in order for this capability to be implemented successfully, we had to think of the end user, so our chemists and engineers, when we were building this capability. So when you break down an HTE experiment, we think of kind of three main pillars. There's the design phase, the execution phase, and the analysis phase. And ultimately, you arrive at your project decision. So in building this capability, we realized that design had to be ultimately intuitive software, and hopefully one piece of kind of an end-to-end design and analysis software that incorporates our HTE fundamentals. On the execution side, because we don't have any specialty groups that are dedicated to instrumentation, we realized that user-friendly protocols and instrumentation that are easy to use would have to be implemented. And then finally, to make it all fit, the analysis has to easily correlate what went into the design with what happened on the analysis side to make it easily readable and understandable. And so Katalyst, when we were developing this with ACD, really hits all marks here. It really guides end users. So these are not necessarily specialized in the art of HTE. Guides end users from the experimental design all the way through to making that informed decision. So it all starts with the design, like Andrew was showing previously. And so just to highlight that, I want to just show how we think of HTE design principles at BMS. And there really are three concepts that you need to incorporate in order to have a successful high-throughput experiment run. The first one is to define your dimensionality. That's how many dimensions you're going to evaluate. So a couple of experiments or examples here are perhaps you want to evaluate solvent versus catalyst or solvent versus base. You could easily imagine a 3, 4, 5 dimension array. And what this does is it really forces you to focus on the question or questions you want to answer. So once you have that dimensionality defined, then you need to compile a list of all of the variables within each dimension. So in this example, it would be a list of reagents, solvents, catalysts, etc. And you need to define that for each dimension. And finally, the last one to really maximize efficiency is to parallelize each of your unit operations in order to do them as quickly and efficiently as possible. And Katalyst really excels at incorporating all three of these design principles. So this is an example where it's very clear to define your dimensionality, like Andrew was showing on the schematic overview here. So it's clear that this is a three-dimensional array or three-dimensional screen, where in this case our dimensions are catalyst, base, and solvent. And moreover, within each of those dimensions, we can start to compile the array of reagents and materials that we're going to be using in our materials table, but also blocked in these groups that make sense from a chemical perspective. So we have catalytic agents, reagents, and solvents compiled here. And then it also enables us to parallelize on the experimental workup by allowing us to, as we saw earlier, define stock solutions and unit operations across, in this case, the 96 well plate. So that's how Katalyst incorporates the design fundamentals. And then we can, at the end of it, tie together all of ACDLabs' powerful technology on the analysis side, where we can now utilize and get kind of a per well resolution of what happened to that reaction. So in this case, we're showing the identity of every component in each well is displayed in a nice visual manner, along with the results of the analysis here. And all of this is done, processed automatically and tagged, and the components are tabulated in this area table here. And what's really nice is you can get kind of a quick visual overview of what happened on the entire plate using some sort of like graphical representation, where in this case, we're looking at product yield over the entire plate. So you can get really a quick snapshot of what happened in the reaction to, again, drive home to that informed decision very, very quickly. So this is really, really powerful technology and really has helped us in implementing this high throughput experimentation capability. But when we started to roll out the software, we did get some pushback from our chemists and engineers. And one of the main deterrents for adopting this technology and the software is really the chemists and engineers not wanting to invest the time to design the plate. If you're designing a plate and you're not very familiar with kind of the methodology, it can be a little daunting. So we realized, and Katalyst has a very nice solution to this, that if we template out certain workflows, we can reduce the end user burden by removing some aspects of the design and kind of removing some of the questions that go into how you actually design such an experiment. And so Katalyst has the ability to make these templates, and what we're doing is we're effectively intercepting this workflow right here, right at the execution stage. So again, all of the questions that the end user might have at the design go away. They're already kind of made for you. So an example would be some workflows that are very standardized and that are done repetitively. So this example is a palladium-CN coupling here, where we have predefined the set of palladium catalysts that are known to work well in these reactions, and we've suggested bases and solvents. So all of the reagents are pre-populated. All of the stock solutions are pre-made at the set concentrations. So all the user has to do is define the starting materials and products for that specific run. Again, all of the dosing operations are predefined. We can even set up an analysis plate with certain analytical functions already predefined for that plate. And the procedures list is also already pre-populated. So the instructions list for how to prepare the solutions, as well as how to dose out the plate, are already predefined, and the user can just simply print those out and be in the lab setting up that experiment in a matter of minutes. So to really demonstrate how useful this this feature can be, I wanted to take this opportunity to make a live demo of the software. So as an example, say a chemist needs to run this type of coupling reaction, a Sonic shear coupling between these two starting materials to make this product, and they want to evaluate all of the variables. So an end user who might not be familiar with how to set up an HTE experiment could be this could be a daunting task. You know, there are 4 dimensions that they want to test: the palladium source, whether or not copper is needed, the identity of the base, and solvent. So it could be overwhelming to start to even think about how you design such a high dimension and complex experiment. But with Katalyst, this is a perfect opportunity to create a template where we know and have defined the dimensions. So the dimensions that we're going to be evaluating are the palladium and ligand combination, whether or not copper is in the reaction, the base and the solvent, and then the array of variables are going to be 6 catalysts. Whether or not copper's in there will be 2. When we look at 2 bases and 4 solvents. So this gives us our 96 combinations. So I'm going to quickly switch over to the software to demonstrate how this would be done. So this is our version of Katalyst that we have at BMS, and this is the Sonic shear template that we have created. So you can see that the catalysts are already populated in there, along with the suggested bases and other reagents that we might need. And so the starting materials are just dummy starting materials that we have. All the user would then need to do is just replace them. So there's a number of options that they can do. They can simply use the drawing feature to draw their structure of choice. So it changes it not only in the reaction scheme, but also in the materials table as well. So let's do the same for this guy. And then we'll quickly just change the product as well. Okay. So as I mentioned, we have predefined sets of reagents that we suggest the user use, but the user can also choose something different. So in this case, let's say the user wanted to try a different organic base. They can choose to query our internally curated database of chemicals. Again, they can search by substructure or by name. Let's just say they want to look at Unix base, for instance. So we search, and this again searches our internal database. We find it there. And then now that's populated in this reagent table, and it's now a line on our materials table. And I'm just going to, for completeness, add the density. Okay. So then we would go to the experiment layout tab. And here again, we've defined all of our set stock solutions that we need, as well as the plates that we're going to use. So in this case, we have one reaction plate with all of the doses out, dosing out on there. And then we have an analysis plate where we've taken an aliquot of the reagents that are in here and applied them to an analysis plate for later workup. So here, the starting materials, the starting material that we put in there have been incorporated with the correct molecular weight and set concentrations already set. But let's say the user wanted to use that different base. They would just go into our preset stock solutions and simply drag and drop to replace, in this case, triethylamine. And you can see the quantities change based on the molecular weight and density to arrive at the proper amount. And so the user could then just do that for every base solution that they needed. And in this case, I have renamed them to something a little easier. They could do whatever looks most readable for them. So then the operations and analysis tab that we saw earlier, all of them have been predefined, so we can set the temperature, how long we want the reaction to go, stir rate, etc., and also the analysis that we want to run. So on this one, I have predefined that we're going to run a UPLC-MS analysis on the plate. So then the execute tab is again all ready to go with the amount of material and necessary reagents required to make all the stock solutions, as well as any procedures, along with some annotations that we add to help the reader. So in a matter of under 5 minutes, someone who wanted to set up close to 96 reactions can be in the lab and running that reaction the same day. So it really is really is paramount to getting our end users, who again are not necessarily skilled or adept at high-throughput experimentation, using this capability. And then lastly, we have that review chevron, where we have a defined analysis plate that's just waiting to receive data from any of our analytical techniques to, again, get them to that informed decision very quickly. So I think now Andrew will demonstrate more of this analysis tab and how they utilize their software to build that.
Right, thank you, Kevin. And wow, it's always good to see the software application running in a customer environment. And I always hold my breath a little bit of like, okay, is everything going to work? And oh, wonderful. So thank you for the demonstration. And I believe it truly represents facilitating high throughput experimentation and almost a democratic accessibility aspect. So that was really helpful for me personally, and I hope for the rest of the attendees of the webinar. What I don't want to cover today is the mechanics of how our systems integrate to the data sources, the instrument data sources. We plan to follow have a follow-on webinar to describe some of the, call it practical mechanics of integrating these various systems. What I want to show is the result of establishing those integrations between systems and what the user experience is like post-integration, okay? So what it looks like, something like this, is Kevin alluded to. So I have the ability to select my plate location. Oops, sorry. Select my plate location on the top left. When I select a individual well, I can see the full breadth of analytical data in one view. And just as an example, we have the ability to show the variety of detector channels on a single screen. So what you see on the left, the right-hand side of the screen is a dynamic analytical display that shows all those channels. There's also visual representations of things like detected peaks and the retention time, as indicated by the numbers above the peak. The shading on the peak itself represents the fact that a peak has been integrated. So depending on your baseline settings as well as your peak detection settings, you'll see whether a peak has been detected and integrated and how that integration's been performed. Furthermore, the dots, the colored dots above the detected and integrated peaks on the screen represent that peak has been assigned or ascribed a particular analyte. And then the color coding on the dot represents what that particular assignment is based on the experimental design, and that specific material can be visualized in that scheme view in the top center of the layout. Like Kevin alluded to, all of the numerical analytical results are captured in the review table. There is sorting and pivoting ability to display different aspects of the design right in the review table. Furthermore, I can export that review table to various applications. It's as simple as clicking an export button. I can even drop that into Excel. I can push it out to other applications via CSV export if that's necessary as well. But the point is, what you get is a fully characterized experiment based on the analytical data that you've acquired, but automatically generating that table. You don't have to use Excel to populate and generate this table. The application does it for you. I can also do some basic math on converting area percent values to ratio values, for example, if I wanted to compare peak area for an analyte to an internal standard, okay? Furthermore, as a former analytical chemist, I like to look at things like stack plots to see any process-related trends that are perhaps observable. So as an example, I can select an entire row of analysis samples, and I can generate a stacked plot using this dynamic analytical display. And again, I can sort between different detector channels and observe whether any of the results might be off and induce things like reprocessing if that's necessary. I don't want to necessarily rely on the numerical output from my analysis unless I have a good sense that the processing is suitable for my particular assay, okay? And that stack plot gives you real flexibility there that I can see the results and gain some trust based on visualizing the results, and then have some good trust based on what's in the review table, okay? Furthermore, I can visualize a variety of different analytical techniques. So here's an example of just displaying some proton NMR data. If I've isolated, say from my initial screen, I've isolated some samples and acquired NMR data, I have the ability to visualize those analysis samples where I've acquired NMR data on it as well. That's important for things like confirming structures and the like. As you may be aware, ACDLabs has a wealth of experience dealing with these different analytical techniques. NMR is a strength of ours. So we do support that strength with the Katalyst application. And finally, as Kevin described, once I feel comfortable with the numbers that I've obtained through my analysis, I can do what I call facile decision support, right? In this case, I have 4 product structures. I'd like to compare the yield of those product structures, those 4 products that I've generated through my reaction conditions, and determining what of the conditions for those individual product structures, what is the best condition for each of those products. Okay, so I can generate that product yield plot automatically with the application. Okay. Well, thanks everyone for making time. Sounds like whether it's for information purposes or for getting some ideas on how to implement practically high throughput experimentation, or maybe some tips and tricks for what you do today. Hopefully you find this stuff relevant. So thank you for making time. I'm happy to transition to the Q&A part of our discussion. But before I do that, Kevin would like to make some acknowledgements based on his colleagues.
Yeah, I just wanted to take a couple minutes to acknowledge the Heritage Cell Gene Experimentation team members for all of their work in kind of helping to get the software off the ground. So the list of key people are here, and I just wanted to acknowledge that this is definitely not a single person operation. It definitely takes a team, so I thank them for all their help.
Lovely. And on behalf of ACDLabs, Kevin, thank you to you and your colleagues there at Celgene, now BMS, for your partnership, your collaboration, and just a great spirit for us working together, and the passion for high throughput experimentation that you and your colleagues have.